Hello everyone, my name is Densul Jung, a PhD student at Post-Tech Computer Vision Lab. I will introduce our work, Levels on the Edges, Selective Quad Attention for Scene Graph Generation, which is joint work with Sang-Hyun Kim, Won-Hwa Kim, and Min-Soo Cho. Here's the summary of our work. We present two novel modules dubbed Edge Selection and Quad Attention modules. Edge selection module selects the relevant edges from a fully connected graph for contextual reasoning. A quad attention module updates node and edge features via four types of attention. Proposed selective quad attention networks with two modules achieve state-of-the-art performances. Scene graph generation is a computer vision task constructing a visually grounded graph from an image whose nodes and edges represent objects and their relationships in the image. In general, the scene graph generation method is composed of three steps. Using a pre-trained object detector, they extract the object bounding boxes and labels. Based on the extracted object bounding boxes and labels, node and edge features are updated by contextual reasoning. Since there is no prior knowledge, contextual reasoning such as GNN and bi-LSTM is performed through the fully connected graph. After contextual reasoning, the updated edge features are passed into classifier and the relationships between objects are classified. This simple framework is very powerful and effective to construct a scene graph, but there are some limitations. First, the contextual reasoning through the fully connected initial graphs is largely distracted by irrelevant objects and their relationship pairs. Here is an example where four objects and four relations in its ground truth scene graph exist in the given image. There are 6 bounding boxes extracted from faster Shannon, 2 of which are from the background. Then the contextual reasoning through the fully connected graph needs to consider 30 potential relations, and 87% of which are not directly related according to the ground truth. These irrelevant relationships may act as distracting outliers. Furthermore, most contextual reasoning methods with graph neural network update node features via edge features and edge features via node features only. Some of them use self-node to node attention but do not capture the various types of interactions. To overcome the first issues, we propose edge selection module which selects relevant edges for contextual reasoning. Also, we propose quad attention module to update node and selective edge features via diverse interactions. I will explain it carefully. In details, proposed selective quad attention network (SQAT) consists of 3 modules: node detection module for object candidates, edge selection module for relevant object pairs, and quad attention module for contextual reasoning. Firstly, following the previous work, we use pre-trained object detectors, fast Shannon, to extract a set of object bounding boxes. And then we construct the initial node and edge features of fully connected initial graph. These node features and fully connected edge features are passed into edge selection module and quad attention module. In order to remove the non-existing or false relationships, the edge selection module predicts a relatedness score Sij for the fully connected edges with a simple NLP. We choose the pairs with top row % highest scores as the valid edges to use in a quad attention module. Lastly, node features and selected edge features are passed into quad attention module. In a quad attention layer, node features are updated via node-to-node attention and node-to-edge attention, while edge features are updated via edge-to-node attention and edge-to-edge attention. In the equation, E sub Q N2E and N2E are the selected edge features from 3 distinct edge selection modules respectively. After several number of quad attention layers, the updated edge features are passed into classifier and the classifier produces sets of predicate probabilities. Each order of the structure of SQAT. Next, we'll take a look at our experimental research. We used the visual genome dataset, which is the most popular dataset for scene graph generation. For your information, I provide the details of the dataset and evaluation metrics in the slides. If you need, then stop the presentation and refer to them. Here is the main results on visual genome dataset. Squat outperforms all the previous work and achieves state-of-the-art on every settings. More specifically, Squat outperforms the state-of-the-art models by a large margin on the scene graph detection setting, which is the most realistic and important setting in practice as there is no perfect object detector. This means that previous work for contextual modeling was most likely distracted by the embedded pairs. Furthermore, to analyze the performance on the complexity of the scene, we divide the image sets in the visual genome into 3 disjoint sets according to the number of objects in the scene. As shown in the table, the squat shows a higher performance gain on the more complex images. The squat is more effective for realistic and complex scenes. Here is the ablation study on edge selection module. We observed that the quad attention module without the edge selection module shows much lower performance than the full model, but shows a higher performance than the BGNN. It shows the effectiveness of the edge selection module and quad attention module itself. We also show the ablation study on quad attention module. The full model with quad attention outperforms the other model variants. Especially, squat without edge-to-edge attention shows worse performance than without edge-to-node attention, since edge-to-edge attention, which is neglected in the previous work, can capture higher level information. Finally, we observe the performance of message passing through various types of graphs. We empirically observe that message passing on fully connected graph is meaningless or even harmful for the scene graph generation. To further investigate the effect of edge selection, we applied message passing through ground truth scene graphs to each model. Every model outperforms state-of-the-art models by a considerable margin. It shows that removing the embedded edges is crucial for the scene graph generation. Lastly, the edge selection module improves the performance of not only squat but also BGNN. It shows that the edge selection module may be a useful plug-and-play module for meaningful message passing. Here is the summary of my presentations. To discuss more, feel free to check out our code and paper online. Thank you for your attention.